Hello everyone, I hope you are doing great. In this tutorial video I want to talk about water waste filtration with COMSOL simulation. Before seeing this video, I hope subscribe my channel and press the ring button to inform the latest video, and please leave your comment in my videos and tell me your opinion. Let us start it. Okay, at first I use a blank model for the simulation, and I add a component, a 2D component. In 2D component I can add for example rectangle, and I provide this these parameters that need for the simulation. I copy all of them and I paste in the parameter section. We have total voltage, DNA, which means diffusion coefficient of sodium, and NAM, and color, which means the chloride, and the temperature and the other parameters that I use a description for them. And in the rectangle section, just I choose a geometry with 3 rectangle and with different widths and height, and just let me choose this value, copy and paste here the widths and the height. Let me widths and height. The height is L, and from the x of minus WCH plus WM, and the Y is 0. I build selected, and you can see the final geometry. For rectangle 2, in the rectangle 2, the width is WCH plus 2 WM, the height is L, and X from the corner is WCH minus plus 2 WM, and divided by 2, and the Y is 0. I use build selected, and you can see the 2 rectangle in the left and right side. And for rectangle 3, I just use a rectangle 3. The width is WCH, and the height is L. From corner minus WCH 0, and I build selected. Maybe let me check all of them. We must symmetry geometry, but I have some mistake. Let me to check it. L minus WCHWM 0 0, and the second is L 0 corner. Okay, and the third is, excuse me for that, it must divide it by 2. And now you can see the symmetry in the geometry. Okay, for considering the effect of filtration in the fluid properties in the solid geometry, you can consider a reservoir that contains water, wastewater that contains the heavy ions, for example, cations, anions, calcium, and magnesium, and other heavy metals, ions. And for this example, we have a membrane. Here we have a membrane, and we have a two selective, cation and anion selective. I will show you how we can consider them. From the physics button, I add physics, I search the tritary, excuse me, I don't know why there is not result. Also we can find it from electrochemistry, I mean this, and we can use TCD, or maybe we can use a tertiary water base with electroneutrality. It means we consider the water-based material, it's better for us, but we can also use different physics. In this simulation, I use this option, tertiary water base with electroneutrality. Okay. Here at first I use group by a space dimension. You can see the space charge. The summation of the charge must be 0. It means you have a neutral condition in your fluid material. And we can add many species here from the basic physics. I can use the number of species 4. In this example, I consider CMG, excuse me, CA, CL, CAS, which means we have 4 types of species: magnesium, calcium, color, and arsenic. These are ions, cations, magnesium and calcium as a cation, and color arsenic as anions. Okay, let me specify the charge of each one of a species. The charge of magnesium is 2, calcium is 2, color is -1, and arsen is -3. As you can see, the total summation of the charges are equal to 0. 2 plus 2 is 4, -1 is plus 3, and -3 is equal to 0. Okay, and from the domains I can use option of ion exchange membrane for anion and cation selective. For example, here I can use the left as cation selective, cation selective, and let me choose the right for onion selective. Okay, and also in electrolyte this is automatically know the electrolyte as here is water, and you can see the velocity. You can specify the velocity as, for example, electron VEL, and we define it later. Let's check the diffusion coefficient. For magnesium we have a dmg. I copy that. For calcium we have dCA, and for color we have dCl. Excuse me. For arsenic we have DAS, and for CH and OH we use the default values, and we leave these values. In ion exchange membrane and in cation selective, for fixed space charge I use CMEM multiplied by F const, which means the Faraday constant. We have a CMEM. The CMEM it means excuse me, let me remove this underline. It means the membrane concentration. We can modify that. It means we have membrane here and also here. Okay, let's check the diffusion coefficient again. dmg, dCA, dCl, and DAS. Okay, and leave another again. And also we can use different volume fraction, but we leave them and we can work on it as a novelty, but we leave them here as a default values. let me choose ion exchange membrane. Simultaneously the CMEM. Also you can use a different membrane concentration, but I use a fixed value for both of the anion and cation selective. Let me multiply this by F const 0, 0. DMG DCA DAS. Okay, and in the boundary condition I can use a periodic condition for the left and right side, and I can use a minus V tot as we define in parameters. Okay, and also we can define electrolyte as inflow and outflow. Inflow it means the flux of ions from the entrance of your maybe reservoir, your container. I use a C0 cation for this, and also C0 cation. It depends on your measurement, it depends on your problem. You can measure the initial ion concentration and do it and input in your simulation and test your simulation and your water filtration to understand it is good for filtration or not. Okay, let me change them to anion C0. The inflow it can be defined maybe from here, or maybe we can just use from here, or it just depends on yourself. Okay, and also the boundary condition, maybe it's better we use downwards, and also for outflow I also add outflow from the top. Okay, it means the filtration was done from here to top. Also you can add some entrance to the middle of these layers, and you can extract the water from the from anywhere that you want. Okay, I use outflow, and let's check the excuse me, for here we can also add apply done on boundary condition. It depends on your problem. Let me define the velocity that we define here, as you can see. Okay, in definition I can add variables. In the variables I can add VEL and VELX for the middle geometry, and variable 2 for here, VLX plus WCH plus WM. It means channel velocity at left, I can duplicate it and just I use a minus instead of plus for the right geometry. Okay, and in the analytics, the definition in the function analytics, I can define VEL. Whenever you want to use the analytic function, you must recall recall the function name. So the COMSOL will find this value and read this value or this variable for your problem. 3. This value was taken from COMSOL AVG plus, multiplied by 1 minus T divided by WCH divided by 2 . And we okay, T, and the function is meter per second, and T from -1 to 1. Which means we have a Gaussian shape of the velocity of fluid, and I don't know why it VEL and T, it's meter and the unit is meter. Let me check the, okay, now it's okay, and you can see the VEL as meter per second. It means it varied by the thickness with geometry. Okay, and now we can Also, we can use electrolyte potential for points for the here, because we have the inflow from here by 0 volt. Okay, in the study I can add the study stationary. I double click on it, I close this button, and from here I can use study extensions. You can vary parameters. For example, I can vary the thicknesses, I can vary the membrane concentration, and let us start to, for example, membrane concentration, and we can, for example, use this code range from 0 to 100, 2000 to, for example, 10,000 mole per cubic meter. Okay, and for mesh, let me check the mesh. The mesh is very important in the simulation when you have 2 dimension, maybe 1 dimension, and also 3 dimension problem. You must consider this fact that mesh is very important, because the old formula, the old equations, the old gradient and derivative were solved on this mesh, and the wrong mesh is caused to some infinity solution that caused the problem for running, and your solution were not convergence to. And it's better for the first use a finer mesh and also physics control mesh for simplicity, but it depends on your geometry. Maybe sometimes you want use a nanometer material, add some nanoparticle in your simulation, and the mesh, in that case the mesh will important. Okay, I go to study 1, then I click compute, and I will wait for seeing the result. In progress you can see the progress percentage, and in convergence you can see the convergence plot that tell you your error bars are convergence or not. It seems the simulation is very good and it will run. Okay, it was run now. You can see the all of concentration, the concentration for example, magnesium, Mg, and calcium, color, and arsenic. Also, we can define new results. I add 1D and I add the line graph. For example, for this line we can add the electrolyte potential, or we can add, I can add define cut line from the, for example, middle, from here to here, or and also you can go to cut line 2D and write the exact value. Okay, for example, I can choose a minus WCH minus WM from L divided by 2, L divided by 2, WCH plus WM. Okay, and you can see the electrolyte potential for all concentration. I can use first, or maybe second, or maybe the last, and also you can use a control and keep the last and first, and you can see, let me show legends. You can see the concentration 0 is shown by blue line, and the other ones is shown by a green line. Okay, for concentration, let me choose a results 1D. I can add, for example, line graph. In line graph, I can also, from cut line 2D, I can remove the expression and replace by new. I go to tertiary current distribution, or Nernst-Blanc equation. You can see all of the species here. For example, you can add fluxes, diffusive flux, convective flux, and electrophoretic flux. It's just depend on your interpretation for your problem. So we can add any physics variable that we needed. Okay, let me, for example, add the concentration gradient in y direction. We can see this curve and the variation in the concentration gradient. Okay, and it is changed by changing the membrane concentration. Okay, the most important parameters for this simulation is rejection. It means in the pure water, we want to have, for example, in ideal case, we want to have 0% of heavy ions, for example, magnesium and calcium. Excuse me, for example, arsenic. It is very bad for body, but some percentage of calcium, magnesium may be good for body. We want to know how much our filtration, water filtration, can reject these heavy ions. For example, 10%, 20%, 90%, or 100%. In ideal case, we want to have 100% for the case that we don't want to have these heavy ions. We can check it by writing this code. Let me show you how we can add, for example, rejection of color, or maybe rejection of arsenic. I can write this code: 1 minus C arsenic divided by C0 onion, and let me to close the parenthesis, and it multiplied by 100. Okay. And we can plot it as the expression CMEM. Okay, it must be based on point graph. I forgot to tell you. Let me add point graph. I can delete this in point graph. Let me add data set, cut point 2D, and in cut point 2D for arsenic, we can add maybe minus 55.0 micrometer L divided by 2. For example, for this point, let me from cut point 2D, and also I must check the one minus CAS C0. Excuse me for that. Maybe it's because we have a two membrane, it must consider when which one you use for the rejection index. And let me show you. Also, it's maybe we better use onion selective here. It must be 61.0. Okay. Okay, you can see it on the right side, and the formula, it must be 1 minus CAS C0 100%, it's okay. Maybe it's better use CAS divided by C0. Okay, and you can see the percentage of rejection for anions or cations. It depends on your definition. Okay, and also maybe sometimes these are changed. I mean, sometimes it means CAS divided by C0 in case you have a point in different direction. You must consider the correct definition for that, and you can see the rejection by increasing the membrane concentration will increase. Okay, I hope enjoyed this video. Please subscribe my channel, press the ring button, and to inform my latest video, leave me your comments, share me your comments, share me your opinions, like my videos, and I hope this video finds you well. This video help you to understand some interpretation for water filtration. Have a good time. Take care. Goodbye.